Good morning, good afternoon or good evening, depending on where you are. My name is Jackie Lynch and I've been working in IT for over 43 years, and my primary focus has always been on performance tuning. Since the middle of 1993, it's been on AIX Performance Tuning. What we're going to cover in this presentation is what I call part one of my AIX Performance Tuning series. And specifically, we're going to cover tuning for CPU and tuning for memory, and then we'll talk a little bit about a starter set of tunables. So the first thing you need to do when you're doing any kind of a performance study is figure out, what are you measuring? Do you care most about response time, or do you care most about throughput? So response time is pretty much from the time I hit return till the time I get something back. But throughput is more of a measure of the amount of work that can be accomplished over some unit of time. This is important because the IBM Power systems are designed for throughput. They're designed to push through as many transactions, as many IOs as possible in a certain period of time. So you need to understand which one of those two things you need to look at so that you know what it is that you're actually trying to measure. Then you have to think about what kind of things make servers go slow. Applications will go slow if they don't have enough CPU, memory, if they don't have enough disk bandwidth, not enough network bandwidth. There's a number of things, including errors. There's the not so obvious specific AIX tuning parameters, some of the Oracle or DB2 parameters. What are your read versus write characteristics? Even things like adapter placement in the server can make a difference if you're starting to push the system to the edge. So how do we start? Well, the first thing is to have a plan, and the plan should first start with some idea of what the problem is and what you hope to accomplish. So step one is describing the problem. Step two is where you have to measure where you're at. We call that taking a baseline. My typical baseline consists of taking a perf PMR, running my own performance scripts that gather data, and making sure that I have up-to-date enmon data. The nice thing about doing the perf PMR is that means that if you do still have a problem after you make your changes, you have before and after data that you can share with IBM. You may even want to add a snap into your baseline. Then you recreate the problem while you gather additional diagnostic data. You analyze the data and then sit down and figure out, okay, what are the different things that I want to change? And you group them and you prioritize them. You do not make all of the changes together. So what I would typically do is figure out which changes belong together, and I will make those as one change, and then I go back and I remeasure and I reanalyze. Did I get the expected impact? If not, then why not? Is the problem being resolved? If not, then we go back to step one. And that's the key thing about tuning. Tuning is iterative. Sometimes you feel like you're in an endless loop, but it's really important that you actually understand that you're going to be going through this process multiple times. This is an example of a performance analysis flowchart. You don't have to use this one, but you do need to have some kind of organized process that you're going to follow to figure out what it is that you're going to tune first. In our case right now, we're going to focus on CPU and memory. This is a basic checklist for doing some performance work. There's a number of things on here that you should be paying attention to. And that's really what this slide here is talking about, how to avoid problems. As an example, any Java prior to Java 7 is not recommended for Power 7 or Power 8. One of the reasons why they recommend a minimum of WAS 8522 is that it actually had an embedded Java, and I think it was Java 1.4, and that version runs very poorly on Power 7 and above. So make sure that you actually do have those things running at the right levels. At this point, we're going to talk about CPU tuning. So we're going to start with a conversation about logical processes and SMT threads and so on. So when I look at my LPAR, I'm either going to have simultaneous multithreading on and set to a particular value, or off. And the valid values for SMT are 1, which is basically off, 2 and 4 and 8, depending on what server you're on. Power 8 and Power 9 you get a SMT 8 as well. So what does that mean? Well, the first thing is you have a virtual processor. Whether you're dedicated or not, And a virtual processor, which shows up as like proc0, is the representation of a physical core. The difference between dedicated and shared cores is that in the dedicated world, if you look at the red arrows, each of those virtual processors actually maps to a real core and is permanently assigned to that core once that LPAR is booted. The only reason it would move to a different core would be if that core failed or something like that. So in our first two examples with LPAR1 and LPAR2, we have two virtual processors. It's dedicated, so we have two physical cores with a one-to-one mapping. If you look at the other two LPARs, you'll see that their virtual processors are shared, and in fact what we have is we have a PU equals 1.2. So that's your entitlement. So when entitlement was specified, in the first LPAR it was specified as 1.2, and in the second LPAR it was specified as 0.8. Those are important to know because if I gave it two virtual processors, which I did, if I look at this first example of where I have a PU equals 1.2, that means that each virtual processor is going to be approximately half of the entitlement. So each virtual processor is worth 0.6 of a core, or 6 milliseconds. When I look at the second LPAR, where I have a PU of 0.8, you'll notice that my virtual processors are worth 0.4 each. Now, the reason this is important is because you'll notice there's no arrows going down to the physical cores. When the LPARs are booted and the virtual processor gets dispatched, it'll dispatch that virtual processor to a physical core. When that virtual processor releases the core, then they put it back on the run queue, and they will always try to dispatch it back to that core. But if you look at the first LPAR, where my PU equals 1.2, the virtual processors add up to more than a single core. So those two virtual processors of 0.6 each will both be dispatched to separate cores. When I look at the last LPAR, you'll notice that each virtual processor is worth 0.4 or 4 milliseconds. They could be dispatched to separate cores, or they could be dispatched to the same core one after the other. That's one of the primary differences between dedicated and shared processor pool. Virtual processors can be dispatched to the same physical core, and it's not a one-to-one permanent mapping. And that can make some difference if you have latency-sensitive workloads. It's important that you understand SMT, or simultaneous multi-threading. With Power 8 and Power 9, you actually get up to 8 threads that can be dispatched via a virtual processor. This is an SMT4 example, but basically the way that it works is I have a primary thread, and that gets dispatched. If I'm running SMT1, I only have primary threads. If I'm running SMT2, I also have a secondary thread. And if I'm running SMT4, then I'll have these tertiaries labeled 2 and 3. Finally, if you're running SMT8, you get another 4 threads. Now, the reason they've done that is because it allows them to duplicate a bunch of registers, so you can run multiple things on the same core when the virtual processor gets dispatched. The key thing is that what gets dispatched is a virtual processor. All the threads associated with that virtual processor get assigned to the same core to run at the same time. Power 9, they made a big change and they added a lot more registers, so actually you get a real big bump when you go to SMT8. Which you weren't getting as big a bump, and you'll see that in a minute when you did that on Power 8. So there was also a change in how they reported on SMT utilization that started at Power 7. At Power 7, the change they made was really to try to show potential spare capacity. Even if only one thread was being used, with Power 6 they used to report that as 100% busy. Now with Power 7 and above, they've changed how it reports the percent busy. So the first CPU with SMT4 on Power 7 shows as 63% busy if it's completely used, and then it adds about 12% more with each one. And there's an uplift from SMT 1 to 2 to 4 to 8, and it's important to understand that, because what it means is if you're not actually using SMT8 as an example on a Power 9, you're leaving about 26% of your RPerf on the table, and its performance you can't use. And in this diagram, which I got from IBM. What this is just showing you is for the Power 8, some of the multi-threading options, really what the difference is. So with SMT1, what you get is the largest unit of execution, so an individual thread will get more time on the core, but you won't get as much throughput. And as you can see, as you move up through the SMT levels, you actually get more throughput, but individual units of work will run for shorter periods of time. So let's touch on dispatching in the shared pool. What happens is the virtual processor gets dispatched to a core, and the first time that virtual processor gets dispatched, that core becomes its home node. I mentioned before that all of the SMT threads go with the VP and run on that core. When that virtual processor runs to the end of its entitlement, so if its entitlement is 0.6, it will get 6 milliseconds on that core. If it has more work to do and no one else wants the core, it gets more core. If it has more work to do, but other virtual processors want the core and they haven't run, then it gets context switched and it gets put back on that home node run queue. If it can't get serviced in a timely manner, it then gets put back onto the global run queue and it could end up running on a different core. But its data might still be in the memory on that home node core. So that's important to understand because this is not something that happens with dedicated cores. What happens as a thread run, as a virtual machine runs, it has to load everything into the cache. When it reaches its entitlement or it runs out of work, that CPU is yielded, and when that CPU is yielded, the cache gets cleared. If I then get redispatched, I have to reload the cache. So here's the problem. If entitlement is too low, then what happens is my dispatch window could be too low. And so if my virtual machine has to run multiple times in that 10 millisecond window, it's never going to run at full speed because the cache has to be warmed up. So the example that I got here, and it's an older one from Nigel Griffiths, but it illustrates the point. If you look at the light blue boxes, and there's 3 of them on the left, that's basically the same virtual machine getting dispatched 3 times in a 10 millisecond window. And what happens each time it's dispatched, it has to warm up the cache, and then it runs at full speed, and then of course someone else takes over the cache, and over time they put their stuff in there. So now I start running again and I have to add my stuff back into the cache. So I'm not running at full speed the whole time, and we end up getting cache misses. So the way to avoid that is to make sure that if a particular workload needs 6 milliseconds every time, then you need to make sure that your entitlement is set such that it gets that. And I talked about SMT utilization a little bit before. And what used to happen with Power 6 was if one of the 2 threads was busy, or 2 of the 2 threads were busy, in both cases it showed as 100% busy, even though because of SMT, you could run about 30% more workload if it was SMT friendly. With Power 7, they changed the reporting so that if only one thread was busy, then it would never report more than 70%, and if the second thread, that's when it went to 100. So with SMT4 and SMT8, they changed the numbers again, and so that you're basically seeing 63, 77, 88, and 100. And then they've done a similar thing with SMT8. So the key point is that what they did was change the reporting, and the idea was to show you how much potential spare capacity you had on a core. I want to talk very quickly about entitlement and virtual processors. Through the different architectures, there have been many changes. As an example, the utilization calculation for when virtual processors get unfolded and so on has changed, and the way it reports on it has changed. So Power 6 and earlier did it one way, Power 7, 8 and 9 now unfold at different levels. What this means is that if you are on a Power 7 or higher, what you will see is more cores activated at lower utilization levels, but you may see higher idle time. And one of the reasons this happens is because they started using raw throughput mode. What raw throughput mode is what I call a spread and stack. Prior to Power 7, what we used to do was we used to load up the first thread of a virtual processor, and then we would load the second thread, and at that point we would then unfold a virtual processor and we would load its threads up, and then we'd unfold the next virtual processor. So what we would see is that the number of active cores would fluctuate. With Power 7 and 8 and 9, we actually activate all the virtual processors and we use the primary thread on all of them. And then when the primary thread gets to a certain level of utilization, we activate the secondary thread. And then we do the tertiaries, and so it's more of a spread and then stack. What this means is that in order to take advantage of all the threads, you are most likely going to have to reduce your virtual processor counts. So if you're looking at an enmon or something like that, and you're only seeing your primary threads in use, and your secondaries and tertiaries are not being used at all, then you probably have too many cores. And if you're comparing it to earlier systems, what you'll actually find is that your percent utilization of actual physical cores consumed is probably going to be the same, but you're going to look like you've got more active cores. So what we have to do is come up with a virtual processor to entitlement ratio. We want to make sure that our entitlement is set high enough so that we can run our workload, and that our virtual processors are set such that we can grow to the size we need to grow to when we peak. But what a lot of people did was they discovered that, well, you can go 10x or 20x. And so they would do that because it gave them the maximum flexibility. The problem is that if you don't get your entitlement right, you actually impact your network, because the shared Ethernet adapter is actually scaled by entitlement, not by virtual processors, and you impact a number of other things. So you want to set your entitlement such that on average or slightly above average, that's what your utilization is, so that's what your entitlement should be. And then your virtual processors should be set to 1.3, 1.4 times max of what that is. Now, Nigel Griffiths has some entries on his blog where he gives some ideas of how you might want to set these. What you do not want to do is set them to 10x or 20x. So you need to put a little bit of common sense in there. If you don't have enough entitlement and you do the 10x or 20x, you'll have a lot of virtual processors contending for the cores, and you'll spend a lot of time dispatching VPs for no reason. The other thing to keep in mind is that every virtual processor has to be dispatched before one can be redispatched. So if you have 20 virtual processors, each one worth like 1 millisecond, every one of those has to be dispatched before the first one can be redispatched. You cannot have more virtual processors in an LPAR than the number of physical processors, and the same applies to the processor pool. If you do that, performance will degrade big time, because every virtual processor has to be dispatched before you can redispatch one, and if you don't have enough cores for that, whether it's in the pool or on the server, then there's always virtual processors waiting. Now, after you upgrade a server, that's when you really want to pay attention to your VPs and entitlements. If I look at the RPerf per core, and then I look at the server that I'm going to, I may see that actually this server is going to require many fewer cores for this particular LPAR. So as an example, if I'm running a P740 or even an 822 with 16 cores or 16 VPs, and I go to a 922, I don't need anything like as many cores. I can probably get by with at least a couple of cores less. I will say that when you're doing the resizing of virtual processors, you should do it LPAR by LPAR based on the RPerf needed per LPAR. So if right now you have a LPAR that's using 24 RPerf when you do the calculation against cores, then that's how many RPerf you want for that LPAR. Do not do it by server size. All right, so if I've got 300 RPerf now, I just go look for a 300 RPerf server. Number one, that doesn't take into account any kind of latent demand, but secondly, with rounding errors and things like that, sometimes you can slightly undersize a server. And the last comment is that too many cores or virtual processors, you're going to spend a lot of time in the dispatcher and the hypervisor with wasting cycles. Now, LPARs can be capped or uncapped. When you're in the shared processor pool, there's several ways that you can cap an LPAR. A capped LPAR can seed unused cycles back, but it can never exceed its entitlement. So basically, whatever you set for the entitlement is the maximum that LPAR can use. There's a number of reasons why people cap LPARs. Sometimes they cap them because the software that they use looks at the maximum setting and looks at whether or not they're capped, and they will charge for the maximum number of processors they can get away with charging for. An uncapped LPAR can go and grow beyond its entitlement up to the size of the processor pool that it's running in, or the total desired virtual processors, whichever is smaller. Any capacity that it doesn't use gets seeded back. All the LPARs in the shared processor pool get assigned a weight, and that weight is from 0 to 255. The default weight is 128. The higher the weight, the more priority that LPAR will get if there is competition to grow. So normally, when an LPAR is running, if it wants to get additional cores and nobody wants them, it's given the additional resource as long as it's entitled to it, and there's no questions asked. But if I'm in a situation where I have two LPARs that need 3 cores each and there's only 3 cores available, LPAR A has a weight of 100 and LPAR B has a weight of 200, what the system does is it sums the two weights, so it's 300, and then LPAR A would get 100 over 300, which is 1 core, and LPAR B would get 200 over 300, which is 2 cores. So the important thing to note is that the weights are share-based. They're not, well, my weight's 200, yours is 100, so I win. So when you're planning your weights, you want to use common sense. So I normally let things default to 128. I'll put my production at somewhere between 160 and 192, and my VIO servers I usually use 255. Whatever it is, you need to have a plan and you need to document it. Now I mentioned capping an LPAR. There's several ways that you can cap an LPAR. One of the ways to cap it is to actually check the box that says capped when you're doing it through the GUI. Another way is to set the LPAR weight to 0. And a lot of people will use the LPAR weight set to 0 because they can change that dynamically. And a third way is to set the desired CPU or entitlement to be the same value as the desired virtual processors. Maximum virtual processors and maximum processors consumed, or CPU, have nothing to do with capping. All they are is the maximum value that you can increase that LPAR to with dynamic LPAR. There are some cases where you are going to want to set those to the same as the desired values, depending on the vendor and how well they understand how IBM's virtualization looks. Some of them may try to actually charge you for the cores in the maximum setting, even though it can't dynamically grow to that. So just watch out for that. Now we talked a little bit about virtual processor unfolding, so I just want to touch on that again. Right, I mentioned that the P5, P6, they load the first and second threads to about 80%, and then they use the next virtual processor. In P7 and P8, they actually changed it and they load that first thread to 49%, and then when it's loaded they go and they kick off the primary thread on the next VP. It's only once it's using all of the processors that it goes back and it starts assigning secondary threads and tertiaries. What this provides you with is the highest per thread throughput and the best response times, but it activates more physical cores. Both systems are going to report the same physical consumption, but what you'll see is that if you don't adjust your VPs when you upgrade, you'll probably see higher idle time, and it will look like more virtual processors are being activated, but they're just not being used. And this is just giving you an example of how it makes the dispatching decisions. So here's our Power 9 SMT8, and we get to about 50% busy, so we kick off another VP. Now in Power 9, there's been another slight change in the dispatcher, and basically if you have a small workload where single threads are using less than 32%, it's going to behave a little bit differently, and it tries to collapse those small workloads. Additionally, on Power 9, SMT8 is now the new default. So if you install a VIO server on a Power 9, you'll see it running in SMT8. Prior to Power 9, everything was running in SMT4, and you had to switch to SMT8. There's also a command called MPstat -v that actually lets you monitor your virtual processor and SMT activity. And so if you look at this, it actually shows you how many virtual processors are actually dispatching, what their utilization is, what their processors consumed is, how busy they are, and so on. And it gives you the dispatch time in milliseconds as well. This comes in at AIX 71TL3 SP2. I mentioned at the very beginning that not all applications run well in the shared processor pool. For the most part, most of the things that you want to run will behave very well in the shared processor pool. And the applications don't have to be aware of micropartitioning. But there are some things that don't benefit. And that comes down to what we just looked at earlier with how virtual processors get dispatched. So because a virtual processor could be dispatched to a different CPU, and because I could end up with two VPs being dispatched one after the other to the same core, I can end up with slightly different latency on those virtual processors. So it can, if anything that is latency sensitive can suffer from that. If you have applications that have polling behavior, if you have applications that are very CPU intensive, and I use SAS as an example, but high performance computing and so on, they benefit much better with dedicated cores. And you can run the tests yourself and figure that out. The applications that are good candidates for micropartitioning, ones with a low average CPU but high peaks, so things that have a lot of range, things like OLTP, web applications mount, most of the things that we run day to day, unless we're doing things like business intelligence and so on. Oracle databases typically run very well in the shared processor pool, as do DB2 and Informix. And one of the other things you may want to do for licensing reasons, you may want to use a separate shared processor pool for databases. I typically will have a pool for databases. Because of the way it gets licensed, I'll have a separate pool for IBM I, and I also look at other applications to determine if they need to have their own pool. We talked a little bit about throughput mode before when I talked about the fact that with Power 7 and above, we now do a spread and stack, where we dispatch every primary thread on every virtual processor before we wrap around and use the second thread. That mode is going to provide the highest per thread throughput and the best response times, but you're going to have more cores. You can switch to scaled mode, and that's going to give you the highest core throughput, but your thread response times might go down. One of the options is to switch to VPM throughput mode 1, which is basically raw mode with a slightly higher threshold for when it kicks off the threads. And then there's the various other scale modes of 2, 4, and 8. I don't recommend that you change to these, but you may have applications that will benefit from them if you are having a problem. And again, if your workloads are not SMT friendly, then you could see an enormous per thread performance degradation by changing these. So it's one of those use with caution type things, but you do have it as an option. As I said, in Power 9, the throughput mode got tweaked just a little bit more. And instead of being 49% or 50% like it was in Power 8, that single thread utilization is now calibrated to 32% in SMT8 and about 44% in SMT4. That basically means that it's going to fall below the dispatch threshold and hopefully lower your physical consumed. I mentioned the MPstat-V before, and this is just an example from one of my systems. This one had 120 cores. Well, logical cores, and it was running SMT8, and you can see all your processor busy, your processor consumed. So the first line shows you overall, what was my processor consumed, and then what percentage of it was I using, and so on. And the VTB is actually the dispatch time for every virtual processor at the physical layer in milliseconds. One of the things that's important to know is how to read something like an lpstat. So in lpstat, it's going to give you virtual CPUs, logical CPUs, SMT threads, and so on. If I look at this, I see that I have SMT4, so I have 4 SMT threads. I have 80 logical CPUs, so I could do the math there and calculate that I actually have 20 virtual processors. It calls them virtual CPUs, but they're virtual processors. So that means I'm going to end up with 20 physical cores being mapped to my virtual processors. And then down the bottom it tells me how much memory, etc. I have. And it also tells me that my entitled capacity is 20. So my entitled capacity and my virtual processors are actually the same. That's because this is a dedicated LPAR. If I look at it for an LPAR that is not dedicated, in this case I have 16 virtual CPUs and 64 logicals, and I'm SMT4. And my entitled capacity is 10. So this LPAR can grow from 10 cores to 16 cores if it needs to. And what's more important is when I look at the pool size is 16. My virtual CPUs is not higher than my pool size, so I'm unlikely to get into a situation where I have more virtual processors than I have cores in the pool. Now with this lpstat example, I'm just trying to illustrate the bad example that I was talking about. This is a shared processor pool. It's SMT4, logical CPU 72. If I divide 72 by 4, I get 18 virtual processors, but my pool is only 17 cores. I'm entitled to 12. I can grow to 18, but I only have 17 to be dispatched across. And the other thing to look at is this APP column. The APP column is actually how many available physical processors are left in the pool right now. And then we have these phantom interrupts, which most people ask me what they are. And basically it's when an interrupt that was designed for another partition that was sharing the same physical processor, maybe it got dispatched for me and did an IO and got context switched. When that IO comes back and I'm running on the core, I basically go, well, that's not for me, so it becomes a phantom interrupt, and then it has to go find where the LPAR is really running. Now this is an example of lpstat with dedicated, so you're not going to see more cores in here than you do have physically because it won't allow you to do that. But I have a logical CPU 80 SMT4, so I have 20 real cores. And my lpstat output looks just a little bit different because it's dedicated, but it does give me things like the percentage of time that I'm spending making hypervisor. And then the sardash mu-p all is just another way of looking at processor utilization. And in this case, what it's showing me is for each of these cores, what my phys is, and then when I add it up, it turns out I'm using 12.71 cores, but my entitlement's only 10. So throughout the time that I was measuring, I was over my entitlement. That's something that I need to pay attention to, because if that's the case most of the time, then I'm going to need to increase my entitlement. MPstat minus S, this is just another way of looking at the same thing. And then I've got a couple examples here of the same data for Power 8 mode. So this is running in SMT8, just to show you the differences. One of the nice things about enmon is that on the LPAR tab, it actually gives you a graph that shows you what your entitlement is, which is the brown line, and then what you're actually using for physical CPU and how many VPs you have unfolded. So this is that example I showed you where I was using 12.71 cores, but my entitlement was 10, and there's 16 cores that I could actually use. Obviously, since throughout this time I was above entitlement, so if this is the case over enough of a period of time, we need to increase the entitlement on this box probably to 14 cores. And this is just showing you with the threads. You can see that only the primary thread on each one of these is used, and so in fact it's currently got 20 cores. So the plan is that we're going to reduce it to 18 and possibly 16, and in fact that's what we did, and we did see a performance improvement, and we did see more pressure on the secondary threads. In this case, this is running SMT8, and we actually didn't change the VPs on this one because we knew that the workload was going to be growing. Another command that's interesting is the VMSTAT-I-W. This adds some additional columns that you don't typically see, and those are the P and W columns. And the P column is the number of threads waiting for I/O messages to raw devices. If you're using a raw devices, that's useful to know. And W gives you the number of threads waiting on file system direct I/O and concurrent I/O. So if you're in an environment like Oracle where you're using concurrent I/O, then you're going to want to have that. The R column is your average number of runnable threads, and that's the global run queue. So it includes the ready and waiting to run plus those running. And then the B column is the number of threads waiting on some kind of resource. It could be memory, it could be I/O. Then additionally we have user and system and processor consumed and entitled capacity. Now user and system are pretty meaningless in a shared processor pool environment, because when you sum them up, they're just the percentage of what was being used at that time of however many cores you had. So you're much better to actually look at processor consumed to see actually how much processor time you're using on average. And then you can compare that to your entitlement. So in this case, my entitlement was 2, and I was using on average 2.42, which puts me at 120% of my entitled capacity. I tend to take the output of VMSTAT capital I, capital W, throw it into a spreadsheet, and then I do calculations down the bottom of minimums, maximums, and averages. And I do the same with run queue and everything else. Now, when we look at this one, the run queue at 71 would throw a red flag for a lot of people, but actually, we have 120 logical CPUs, and this system, if you look at VMSTAT-V, has 15 memory pools. Every memory pool has its own LRU, least recently used daemon. So we know that from the starting point, we have at least 15 LRUs. We have 120 logical CPUs, so that run queue would consist of the LRUDs, things that are running, things that are waiting to run. So 71 might not be a bad number. That's why you need to monitor the system and just look to make sure that there's nothing strange going on across the board. If you want to monitor the shared processor pool, then there's a flag on the HMC which you can change dynamically, and it's called Allow Performance Information Collection. So you need to go into the HMC, and on every LPAR, click on Properties, go down to Advanced, and check the box to allow that. If you don't do that, then Topaz minus capital C or the enmon option P, which monitor the pool, can't provide you with proper pool monitoring. Additionally, when you run an lpstat, you're not going to see anything worth seeing in the APP column or the pool size because it can't look at everything across the board. It is not turned on by default, and it's something that I typically will turn on to every LPAR. This is an example of what you'll see in a Topaz-capital C. Shows you the pool size and the APP, so I've got 16 available processors. You can see my virtual context switches. I monitor those virtual context switches because if I start to see a lot of those, it's an indication that an LPAR may not have enough entitlement. So typically you'll see a lot of virtual context switches when your percentage of entitlement is too high. The enmon-P shows you a very similar thing. It's monitoring the pools. So again, this is just showing me for a particular LPAR how many CPUs are in the pool and how many of them are used and so on. And another way to look at it is with the LPAR tab in enmon. The last thing I want to talk about in CPU is the EMSTAT command. And one of the reasons for that is if you bring old code across without recompiling it, you can end up running into emulation and alignment issues. If they've changed the code such that the particular commands you're using don't exist anymore, then it will find something to emulate it. And if you start seeing numbers in here, that is absolutely going to be impacting your performance. IBM states that things that were compiled on earlier architectures and operating systems will be binary compatible with ones in the future, and that is true. You will never see anything in that binary compatibility statement saying, oh, and yeah, it'll perform well. So if you're seeing a lot of emulation and alignment numbers in the EMSTAT command, then you really want to go look at your application to see what's going on and why those are happening. And then just some general server sizing thoughts. Making sure you have enough CPU. We'll talk about memory. Making sure that your min desired and max settings are set correctly. We're going to talk about a lot of the memory things, whether or not you're going to run shared or dedicated, capped or uncapped, and so on. Probably the most important thing is do not starve your VIO servers. If you are running virtualized, then you need to make sure that those VIO servers have enough memory and enough CPU, or they're going to run very badly, and that will impact the performance for every LPAR. I've already talked about CPU sizing before. The key thing you have to do is make sure that you size by concurrent peaks. If you're buying a server that you want to run 4 LPARs on, and they tend to peak at different times, that's great. But if they all peak at the same time, which is fairly common, you need to make sure you have enough cores to deal with the peaks when they all occur concurrently. And that's really what this is illustrating. So somebody looking at this might have said, well, if I look at the entitlements, and I see people do this all the time, they sum the entitlements, I only need 11 cores. But actually, if you look at this, at noon every day, those 4 LPARs peak at 20.5 cores. You need 21 cores to run this workload. Never, ever size by entitlement. At this point, we're going to move forward and we're going to start to talk about memory. So there are 3 types of memory. There's kernel memory, persistent memory, and working storage. So kernel memory is AIX itself. The minimum's around 2 gig. It varies depending on what you put in the kernel. Persistent memory is the stuff that's backed by file systems. We call it the file cache. It is basically everything that you're reading in and out except that raw devices, GPFS or spectrum scale, Oracle ASM, those do not make use of the file cache. This is a number that fluctuates depending on how much I/O you have coming in and whether or not you're using concurrent I/O or direct I/O and a number of other things. And then we have working storage, and working storage is dynamic. That's where your executables and your work areas and all those things go. And it's backed by page space. If you look at the AVM and a VMSTAT, that's where you're going to find your working storage. It's also known as computational, and it shows up as % computational enmon analyzer or percentage of memory used for computational in VMSTAT-V. When it starts to get close to 97%, you're going to be paging and need more memory, so you really do want to pay attention to that computational, and personally I pay attention to it when it gets close to 80%. You never want to steal from working storage if possible. Working storage is expensive because if I'm stealing from working storage, I have to page it out first to a page space before I can free that page to make it available. That's different to persistent storage where, because I read it in from a disk, as long as I haven't modified it, I can just take that page, and then if I need that page again, I can read it back in from disk. I don't have to write it out first. How the decisions are made about what to steal from and when, these are impacted by min, perm, max client, LOU file repage, and page steal method. One of the things that you need to do when you're planning for memory is you need to plan for firmware overhead. What I see all the time is people will add up the memory they need for their LPAR and they'll buy a server with that much memory. The problem is that you need to make sure that you have enough memory to deal with all the high-speed adapters that you may have, as well as the overhead caused by your maximum memory settings. I have a spreadsheet that I use. You can use the system planning or whatever, but basically every active port on an 8 gig card or higher, so think 1632, those high performance cards, every active port requires 512 meg in the VIO or LPAR. So if they're in a VIO, the overhead goes there, but if they're actually physically in an LPAR, the overhead goes there. Additionally, if you're using NPIV, every virtual fiber channel or MPIV VFC host will require 140 meg in the VIO on top of that 512 meg for the card port. That may not sound like a lot, but if you have 40, 50, 60 VFCs, that can add up very quickly. So you need to make sure that you include those in your calculations, and that way you should be able to make sure that you don't underestimate your memory overhead. The reserve memory in the system is based on the maximum memory setting for an LPAR, not on the desired. The reason for that is these things called hypervisor page tables. So the system has to make a mapping of virtual memory, which is what it looks like within the LPAR, to the physical real memory. And it does that using hypervisor page tables. For every LPAR, there's a hypervisor page table built, and it's based on that maximum setting divided by 64 or 128 and then rounded up. So if you set for a 5 gig LPAR 100 gig, you are going to be wasting a lot of memory. And here's some examples. If you look at this, this is from a enmon analyzer, sorry, HMC scanner. If you look at the firmware gigabytes, that's where this overhead was going to show up. The system will take its memory for memory overhead before you get yours. And the things that will affect it, as I said, are those maximum memory settings, as well as whether or not you're doing memory mirroring. So the spreadsheet that I use basically has me put in how much memory is in the box, what the LMB size is, which is also known as the memory region option, how many high performance adapter ports per BIO, how many VFCs. There's also a little bit of memory needed for IO draws. And then I always throw in a safety net, whether or not I'm using active memory mirroring and so on. And then it does a calculation, and it basically tells me how much memory I really need. So if I look at this, I had 384 gig and I was going to activate 190 because my desired came to 185. But actually, when I add in the overhead for the high performance ports and MPIV, plus the overhead for IO draws and the hypervisor itself, which is at least 1.5 gig, and my safety net, I actually need closer to 203 gig. It's very easy to underestimate how much memory you need. You never ever size your memory by desired, and make sure that when you do that maximum memory calculation that you use something with common sense. You know, a 5 gig LPAR is never going to grow to 100 gig. I mentioned LAU file repage. Basically that sets the rules for how the system determines who to steal from. And the only reason I mention AIX 5.3 in this is because if you've done an upgrade from 5.3, then anything that was set there in tunables will be brought across the way it was, and the way it was incorrect. What LAU file repage does is it says my min perm always is going to be set to 3%, and anytime that file systems are using more than 3%, I'll try to steal from file systems. Max perm and max client should be set to 90%. If they are not set to 90%, you should change them to that, unless you have something in writing from IBM that says that even though you're running on AIX version 7, you should change these. So max perm is a soft cap on the amount of memory that file systems and network use, and it affects everything: JFS, NFS, JFS2, the network. Max client is a hard cap, and it specifically affects JFS2 and NFS. Now, Pagedeal method has to do with when and how the LAU daemon scans and frees up pages. So prior to version 6, by default, there was memory pools, and each memory pool was just a whole bunch of pages, both persistent and dynamic. When Pagedeal method is set to 1, which is the new default, what that does is it actually keeps 2 sets of pages for each memory pool. One is dynamic and one is working storage. When Pagedeal method is set to 1, it will go through and it will scan only the file system pages to try to find pages to free. It won't look at those working storage ones unless it cannot get what it needs out of file system pages. That can have a significant impact on how quickly you get pages resolved. So if I use this as an example, I have 500 gig of memory and I'm doing easy math, and 50% is file systems, 50% is working storage, and I have 5 memory pools. So I have at least 5 LAU daemons, 1 per memory pool, each controlling about 100 gig of memory. If I have Pagedeal method set to 0, I will scan all 100 gig of memory in every pool. But if it's set to 1, I'm only going to scan 50 gig in each pool that is used by file systems. That's going to reduce my CPU that is used for scanning, because that CPU comes out of your LPAR significantly. If you combine this with concurrent I/O, it can make a significant difference to your performance. The one thing you don't want to see in your system is paging. And in a VIO server, you never want to see paging. So there's a couple of rules about paging that you want to pay attention to. The first thing is you do want to have more than one page volume. It used to be that most of the kernel stuff went to HD6, so you had to pay a lot of attention to that. The reality is that all of your page spaces should be the same size, because some of the kernel pages can go outside of HD6 now. Your page spaces should all be on different disks to each other. The last thing you want to have happen if you actually start paging is that the system is trying to write to all of the page spaces at the same time, and they're on the same disk. If it's internal, that means the CCAR is going to be moving around, and if they're on the SAN, which there's no reason they can't be on the SAN, then you run the risk that you're going to have like long queue depths. So you want to have multiple page volumes, and you want to have them on different disks. Don't put them on busy disks. You do not put page space on your Oracle redo log disk. When you mirror root VG, it will mirror HD6 for you, and you should leave it mirrored. In terms of memory, you can use SBmon-G to get a breakdown of what your memory looks like. So in this case, I have 512 gig of memory, 263 gigs in use. I got 40 gig of page space. I got 56 gig pinned. Now, when I see a number like 56 gig pinned, the first thing I suspect is that I'm probably on a system with a database like Oracle, and it's probably gone and pinned the SGA or PGA. And then I can get a breakdown of like the size of the pages and how much of that's pinned and so on. I can actually specify unit equals auto so that it puts it into human readable format. So in this case, it put it all out in gigabytes, and from this I can get an idea of what it's actually doing with something that's more meaningful. And then you can also get a lot more detail about domain affinity and how the memory is allocated across the CPUs. So there's actually a significant amount of memory information available. And when you're looking for memory problems, you've got the lsSRAD command, you've got MPstat, you've got topaz, svmon, and a number of other commands. The things that you're going to want to look at your computational use, or your percent computational, or your VMSTAT. Again, we've talked about this, but when your computational gets close to 97%, you will be paging and you will need more memory. So I start to worry about it when it gets to about 80%, so that I have time to add the extra memory before things go south. You could see this in the enmon analyzer in the memnew tab. The red here is my processor, so I'm using, it's about 65% or something of memory is being used by CPU. In this particular case here, you can see the purple line is my percent computational, and it's right on 89.85%. So this system really does need some more memory. And this is just an example with a lot of file system caching. So you can see here this one's doing a lot of I/O, and its computational is a bit lower. One of the final topics I want to talk about is affinity. So when we're looking at memory, and we start to get into some of these multi-node systems like 950s where they have multiple sockets, or 980s where we have multiple nodes, we have to start worrying about things like affinity. A lot of changes have been made to affinity to make sure that it tries to put things together where the CPUs and the memory all go together. But there are some things you can do to help yourself. If I look at this layout here, and this is 4 sockets and 4 nodes. So when I look at it, when the memory gets installed in the system, the DIMMs are actually assigned to physical cores. You can see here I've got 7 memory where there's no DIMMs. So what that means is if something's running on the core on the top right, it's got memory DIMMs associated with it. But if they're running on the cores just to the left of that, there's no memory DIMMs associated. So in order to be used, I have to go and get memory from one of the other cores. And that means I'm going to another core on the same chip, another socket, or worst case another node. And there's different latencies involved in doing that. So if you really care about memory performance, it's normally recommended that you fill every DIMM slot. You can tell if you've got this problem when you run the MPstat-DW. So here we have local, near, and far. What does that mean? Well, when I look at local, that's S3HRD. What that says is that 100% of my memory accesses for that CPU were on the same chip. For near, it means that they're in the same socket. And actually for far, it means the same thing. When it's an E880 or an E980 where it's multi-node, far is actually that it's in the other node. And there's a significant millisecond latency impact of doing that. So if you look down the bottom, you can see that I'm actually starting with some of my logical CPUs to actually end up going to some of to different sockets to get some of my memory. On my 880, you could see that I have 120 logical CPUs, and in this case, local same socket, near is same node, and far is a different node. So it looks like I'm getting everything from within the same node, but that I am getting some stuff where I'm having to go across a socket to get the memory. So the moral of the story is, if you have 16 cores in a socket, try not to run LPARs that have more than 16 cores in them, because that 17th core is going to be in another socket or it's going to be in another node, and you'll take a latency hit for that. In the old days, we used to talk about setting some of these tunables. Only reason I'm showing you these is because if you did a migration from AIX 5.3 and then have continued to upgrade all the way to version 7, some of these may be set and you do not want them set. The only settings that you should be using in version 6 and 7 and above are min-free, max-free, and then there may be a couple of other things that you want to tweak. And you can find what the settings are in /etc/tunable/nextboot. I typically calculate min-free and max-free. I very rarely set any other memory or I/O settings within my IOO and VMO commands unless there's a specific need for it that I've talked to IBM about. Now if we run a VMSTAT -v, and in this case here, you'll see that I have the default settings and about half my memory is being used for file systems. There's 5 lines, there's actually 6 lines that are really important towards the bottom of it. These are all since boot. So you can see pending disk IOs blocked with no PS buffs, paging space IOs blocked with no PS buffs. Then the next couple have almost nothing, and then there's external pager file system IOs. So the P buffs are pinned memory buffers, and basically when I go to build an IO, the first thing I do is request a pinned memory buffer for that volume group. I then start to build my IO. If it's a paging IO, I then have to request a page space buffer. If it's a JFS2 IO, I request a JFS2 buffer, which is an external pager file system buffer. I have no idea why they called it that. What we're seeing here is this system's in trouble. It's running out of P buffs, it's running out of page space, and it's running out of JFS2 buffers. Now, we don't know when the system got rebooted since it's since boot, but I believe it had been about 3 days. So the system had some serious problems and we needed to do some tuning. The P buffs I cover in my IO presentation, but those are fixed using the lvmo command, and you add more P buffs to the specific volume group that has a problem. Page space buffers, there's only a couple of ways to fix them. One is to add additional page spaces that are the same size. The other is to increase the size of the page spaces and shut down the system and reboot. You can swap off a page space, increase the size and swap it back on, but if you've got a paging problem at the time and you swap off that page space, you'll probably crash because you'll probably run out of page space. And then JFS2 buffers, those are fixed with the IOO command, and again I cover those in my IO presentation. So this is an example of a system that was actually having paging problems, and because it was having paging problems it was backing up the P buffs, and it had been up 16 days, so it had 453 or 4.53 million actually page space IOs blocked. You don't want to see that. And it had 4 memory pools, and as I said, it had been 16 days. Also, if you look down here, you'll see that 89.9% of memory was used for computational. This is probably a classic example of an LPAR that needs more memory and that also needs more page space. Now, I've mentioned memory pools a couple of times. If you look at the free column, you'll see in this particular case I have 9,902 free pages. What most people don't understand is that that is the total number of pages, and you need to divide it by the number of memory pools to figure out what the impact of min free and max free will be. By default, min free is 960 and max free is 1088. So in the case I'm giving, I had changed max free to 2000. Because I only have 10 memory pools, I have to take that 9902 and divide it by 10, so each memory pool on average has about 990 pages free. Well, my min free is set to 960 and my max free is set to 2000. If I've only got 990 pages free, I am right in between them, which means I am page stealing, and if I drop down to 960, I will start page thrashing. So I can see that because I'm starting to see some page in and page outs. So this is a system where I would want to pay close attention to my min free and max free, and I might want to bump them up. I may also want to add some more memory depending on what's going on, but we are definitely short of memory. So how do you calculate min free and max free? The typical calculation that I use is min free is the maximum of 960 or 120 times the number of logical CPUs divided by the memory pools. And then max free is a similar calculation. But I also round them. So if max free comes to 1472, I'll probably bump it to 1536 or 2048. You shouldn't have a difference between min free and max free that's more than 1000. That's according to IBM. If you want to use numbers greater than that, then you should talk to IBM. If you make them too big, then you'll start to see really high values in the free column, but you'll actually be paging because you've set it such that it starts paging sooner. So the idea of changing them is to have a slightly bigger gap to give yourself a little bit more wiggle room, but you don't want to change the gap to be so big that you create a problem. In terms of monitoring, the tool that I use a lot is enmon, and the top enmon that you see in red is the one that I use for a quick 30-minute enmon snapshot, and I've got a description of all the flags there. And then the one that I use, 724, I run all the time, is the one where I have a snapshot every 150 seconds and I take 576 of them. And lastly, I want to point you to the Power 9 Performance Best Practices document. IBM has this published. There's also a Power 8 version of it, and it has a lot of tips in here for you. With that, I'd like to thank you for listening to this session. I hope that you found it useful, and if you have any questions, please don't hesitate to ask. I will be uploading this to my movies website at YouTube, and I've also put a link in here for the handout in case you need to get a copy. Thank you, and have a wonderful week.